Hello everybody. We are going to start the next part of the chapter, which is the material balance for reactive systems, and the difference between what we are going to cover now and what we covered before is um, uh, the terms of reaction that were in the mass balance equation that we didn't include before. So in the beginning of this chapter, we said that the mass balance equation consists of 5 terms. We said that there is term for the feed to the unit, the product, and then we said that there is a unit or a term for production or generation and term for consumption. And these are the 4 terms for steady state, and if it's unsteady state, we said we will add a term which is the accumulation term. So this is the basic equation, and for the last, I would say, 10 videos or so, we were just focusing on the terms of the feed and the product, and all the equations that we were writing were using were the mass in equals mass out, or number of moles in equals number of moles out. And this was okay because we had no reaction and we were operating under steady state conditions. So this is the equation in this condition. But if we have a reaction, then we should include the terms of the generation and consumption. And before we go into the details of the of these terms and how we can include them in the mass balance equation, we need first to do some quick revision on some basic terminologies and basic concepts related to chemical reactions. They're very, very important. They're very basic, so I assume that most of the audiences will be aware of these terms, and it would be kind of repeated information, but it's important to make sure that all these information are clear and we agree on all these information and we are all on the same page. So the first thing is what we call the chemical reaction stoichiometry. So the stoichiometry is a term that's commonly used for to refer to the balance of the equation, meaning that if you have an equation like this, then the equation is reaction between methane and water to produce carbon monoxide and hydrogen, and it's clear that from the equation that we have, that there are some numbers. There are numbers that are not written, and if it's not written, then it means it's 1 molecule of methane reacts with 1 molecule of water to produce 1 molecule of carbon monoxide and 3 molecules of hydrogen. So these numbers are called the stoichiometric coefficients, and the balanced equation is called the stoichiometric equation. This is what we understand from this equation, or what this equation is telling us, that 1 molecule or 1 mole reacts with 1 mole or molecule to produce 1 and 3. The reaction to be used, it's very, very important. It's very important for the chemical reaction to be, or the chemical equation to be, a balanced equation. Meaning that the number of atoms of each species in the reactants must be equal to that in the product. So for example, this equation that we have here, we have aluminum reacting with water to produce aluminum oxide and hydrogen. There is already a reaction that goes like this. The aluminum can react with water to produce aluminum oxide and hydrogen, but this equation is not balanced because we have only 1 aluminum atom in the reactant, and we have 2 aluminum atoms in the product. We have 1 oxygen and we have 3 oxygen in the product. The hydrogen is okay, but we have to make sure that all the elements are balanced. So we have to rewrite the equation to make sure that the equation is balanced. So what we will do is we know that it's Al2O3, so there must be 2 aluminum, so I will add 2 here, so the coefficient of aluminum would be 2, and we know that there are 3 oxygens, so I would put coefficient of 3 here. So I have 3 oxygens, I have 2 aluminum, but I have 6 hydrogens, so I will have 3H2. So looking at this equation now, it's balanced, meaning that the each atom has the same number of or each species has the same number, or each element has the same number of atoms in the feed or in the reactant and in the product. So we are going to use the stoichiometric coefficients a lot in this chapter. So we refer to the stoichiometric coefficient with the symbol nu, which is this symbol. This is a Greek symbol that is equivalent to N in English, so it's nu in the Greek letters. And this symbol is going to refer to the stoichiometric coefficients, and it has units of moles. Okay, and nu is negative for reactants and positive for products. So this is something that we have to keep in mind. This is very important. We are going to use this this coefficient a lot. It's going to be a very, very basic term in the equations for or the terms of the generation and consumption. So we need to keep this in mind, that nu is the stoichiometric coefficient. It's positive for products, negative for reactants. So for this equation, the we have four compounds, so or four species. So for aluminum, the coefficient is -2. For water, it's -3. For aluminum oxide, it's +1. For hydrogen, it is +3. These are positive because they are products. So there is one other thing that we can learn from the reaction, which is, or we know about the reaction, it's the stoichiometric ratios. So the stoichiometric ratio of two molecular species participating in a reaction is the ratio of the absolute value, and this is important, that's the absolute value of their stoichiometric coefficients in the balanced equation. And it's important, it's very important. So it's the same thing, it's just the ratio of aluminum to water, it's 2 to 3, it's just this. But this ratio is important because it can help us to calculate the amount of other reactants or products given one of the reactants or the product. And for example, we have here 2A plus B goes to 3C and 4D. And whatever A, B, C, and D are, but we have four species in this reaction. A reacts with B to produce C and D. And if I look at the reaction, and if it's a stoichiometric reaction, then I know that, again, this is all based on the balance of the equation, or the stoichiometric coefficient, that 2 molecules of A react with 1 molecule, or moles of A react with 1 mole of B, producing 3 moles of C and 4 moles of D. So if I know that the number of moles that got consumed in this reaction are 10 moles, then I know I can calculate myself the number of molecules of B, or I'm sorry, number of moles of B that are consumed, and the number of moles of C and D that are produced. And this is just cross multiplication. So it's ratio 2 to 1, so it's 10 to 5, which is 10 multiplied by 1 over 2, 10 times 1 over 2. The same here. So I need 5 molecules of B producing 15 C, and moles of 5 moles of B producing 15 moles of C and 20 moles of D. This is all these three numbers are got by the balance of the equation, just using the stoichiometric coefficients or the stoichiometric ratios. There is a very important note about this, which is that the balance of the reaction is balance based on the moles or molecules. It's not mass. So this is very important, and this is what I was saying, that the ratios here are 2 molecules or 2 moles, and this is 1 mole, this is 3 moles, this is 4 moles. So this is ratio of moles, and we cannot use this ratio for masses. For example, if we know that this reaction takes place of sulfur reacting with oxygen producing sulfur trioxide, and that we know that the number of, or the mass of sulfur that is consumed is 120 grams, and we need to calculate the mass of oxygen and the mass of consumed and the mass of sulfur trioxide that is produced. So we cannot say that the ratio is 2 to 3 to 2, so we have 120 and do what we did in the previous slide. It's not possible. The ratios are by moles, so I have to convert this mass that we have here into moles. We can simply do this because we know the atomic weights of sulfur and oxygen. So from this we can calculate the molecular weight of oxygen, the molecular weight of sulfur trioxide. It's just simple math, and from this we can calculate the number of moles of sulfur that enters the reaction. We have 120 grams, and one mole is 32 grams, so this is 3.75 gram moles. And now I can use this number for calculating the number of moles of oxygen and sulfur trioxide based on the stoichiometric ratio. So I know the ratio is 2 to 3, so the number of moles of oxygen is 3.75, which is sulfur, multiplied by 3 over 2, which will be 5.625. And from this we can calculate the mass, which is what I'm asked to calculate, which is multiplied again by the molecular weight, but in this case molecular weight of oxygen, because this is mass of oxygen. The same for sulfur trioxide, it's 2 to 2, which is 1 to 1, so it's the same number of moles, and we multiply it by the molecular weight of SO3. So now we calculated the masses, and it's 180 grams and 300 grams, 420 grams of sulfur that is consumed. There is another option, which is a valid option, and this option is saying that we know that the ratio by moles is 2 to 3 to 2, and these 2 moles are equivalent to 64 grams, okay, and this 3 moles are equivalent to 96 grams, and these 2 moles are equivalent to 160 grams. So what I have here is a ratio, but this is a ratio by masses, not by moles, which is something I can use with masses. So I know that 64 grams of sulfur react with 96 grams of oxygen, producing 160 grams of SO3. So I can put this 120 grams, and from the ratios directly I can calculate the mass of oxygen and the mass of SO3. Okay, so this is another approach that you can use. Either way, it's going to produce the same thing. These are the same numbers that we saw here. Oxygen 180 grams, SO3 300 grams, and this is what we have here. There is one thing that is worth mentioning here, which is that the reaction maintains the conservation of mass, meaning that the mass is of reactants is equal to the mass of products. Here I have 6496, it's 160, or 120 plus 180 produce 300. So it's the same mass. It doesn't matter if this is a reaction or a simple reaction or a complex reaction. The mass has to be conserved. Of course, the moles is not conserved, and this is an important difference between mass and or reactive and non-reactive system. In the reactive system, we said it doesn't matter, you want to apply it with mass, apply it with mole, it's fine. But here we have to be careful that for this reaction, the reaction starts with 5 moles and it produces only 2 moles. So the number of moles is not conserved. What is conserved is the mass. Okay. So this is the first thing that, or the first things that we want to mention about the stoichiometry of the reaction, the stoichiometric coefficients, the ratios, and how we can use them to calculate unknown number of moles or masses based on the balance of the equation and one information about one of the reactants or products. In the next video, we will continue discussing these basic topics, and I'll see you then. Goodbye.